Hello, I am Lorenzo Dall'Amico. Thank you for attending my presentation. Today I'm going to talk to you about the optimal Laplacian regularization for sparse spectral community detection, which is joint work with Couillet and Nicolas Tremblay. So what is community detection? Consider an undirected and unweighted graph in which the pairwise interaction among the nodes is represented by the edges of this graph. Then real social graphs tend to be structured into communities, clusters. Our problem is that we want to retrieve these communities given the representation of the graph. Here we have an example of the dolphin network in which the dolphins socialized into two different communities, which are here labeled by the different color code. More formally, given a graph with n nodes and k communities, we want to assign to each node the correct class labels. So we have the adjacency matrix, which is the entry ij is equal to 1 if the node I is connected to node j, here represented in white, and is equal to 0 otherwise, here in black. On the left, we have the problem, which is our input, the adjacency matrix, a representation of the graph. Whereas on the right, we have the solution, which is the same adjacency matrix, but in the proper base, in which it is evidenced that nodes belonging to the same community tend to be connected more often than across communities. So what is spectral clustering? It consists of a node embedding to a low-dimensional space. Each node is projected to a low-dimensional space using the eigenvectors of a specific matrix. Once this embedding has been performed, one can use some small dimensional clustering algorithm like k-means to finally assign the class labels to each node. So as an example, we can consider the random walk Laplacian matrix. First, in the dense regime in which the average degree, the average number of connection grows with the size of the network. So here we have two isolated eigenvalues. If we look into the eigenvector attached to the second largest, this is what it looks like. We have 5,000 nodes, and the ith entry of this eigenvector, the sign of the ith entry gives information on the community of the node I, which is a small dimensional embedding. On the other hand, if we have a sparse network where the average degree is independent of the size of the network, this is what the spectrum of the random walk Laplacian looks like. This matrix, as many others, have a bulk that tends to spread. And if we look into the eigenvector attached to the second largest eigenvalue, this is what it looks like. It does not contain information on the class structure at all. So spectral clustering on sparse graphs is hard. Why do we care? Because real networks tend indeed to be sparse and also to be heterogeneous in the degree distribution, in the sense that we might have in the same network hubs as well as leaves. So to keep into account of both these aspects, we consider the degree corrected stochastic block model, where we have n nodes. We will talk about k equal to 2 communities for simplicity, but we studied the case of arbitrary k. Sigma I is the label of node I, which can be -1 or +1 according to which class it belongs to. C is the class affinity matrix. Then each edge is created independently, and the node I is connected to node J with probability given by this probability distribution, which is proportional to theta I, theta J. The larger is theta I, the more connection the node I will have. The probability distribution of theta is the same as the probability distribution of the degrees. Then we have the class structure. When sigma I is equal to sigma j, so the two nodes ij are in the same community, we are on the diagonal of the matrix C, and they get connected with the probability proportional to C in and C out otherwise. The closer C in is to C out, the harder is the detection problem. The concept of hardness is very well established in the literature. We introduce C, the expected average degree, and phi, the second moment of the theta. The larger is phi, the broader is the degree distribution, then non-trivial label assignment can be done if and only if alpha is larger than a critical value, where alpha is a parameter that depends on C in minus C out. So if alpha is smaller than this critical value, we cannot do better than random guess. Whereas as soon as it is larger than the critical value, we can do something non-trivial. We will call this the detectability threshold. Now, this is an incomplete state of the art. The DCSBM can be solved asymptotically, optimally using belief propagation equations, which are denoted with BP. They are a set of fixed point nonlinear equations, which are not guaranteed to converge for an arbitrary graph and an arbitrary initial condition. And the closer we are to the detectability threshold, the longer it takes for this algorithm to converge. We can obtain suboptimal but still very good solution using a linearization of belief propagation, which leads to a spectral algorithm, which does not need to converge, that is based on the non-backtracking matrix, which is a large matrix which can be used to perform community detection. This matrix has a connection, thanks to the Hiarbas formula, to the Pathstation matrix, which depends on the parameter R. We studied already this matrix and showed that the optimal parameterization of this matrix should be a function of the hardness of the problem, which we recall is alpha. And so the optimal parameterization is each age zeta alpha. Other methods are based on the graph Laplacian d minus a, the random walk Laplacian, or specifically for sparse networks, the regularized Laplacian L tau. So our ultimate goal is to find a unified framework to explain all these methods at once. So the non-backtracking matrix is a matrix of size the directed number of edges of the graph. The entries are the edges. So we have that the entry ijkl is equal to 1 if there is a non-backtracking path from I to L, meaning that I is different from L. The eigenvalues of this matrix are complex because it is not symmetric, and most of them are bound by a circle in the complex plane. Only 2 of them are larger and they are real. This matrix was initially proposed to perform community detection by using the eigenvector attached to the second largest eigenvalue. What we showed is that by linearizing belief propagation, you obtain the fixed point, the eigenvalue equation number 1, where it suggests that zeta of alpha, which I recall is a function of the hardness of the problem, is indeed an eigenvalue of this matrix, which is inside the bulk. And the corresponding eigenvector can be used as well to do community detection. Now, for easy problems, alpha is large and zeta alpha tends to 1, whereas it increases, zeta alpha increases for hard problems. Now, both the inside and outside eigenvalue of B can be used to do community detection as soon as theoretically possible. And the eigenvalue inside the bulk introduces naturally the parameter zeta of alpha, creating the first connection with this parameter, which will be fundamental to connect all the other methods together. Now, the Pathstation matrix has a direct connection with the non-backtracking matrix, and in particular, zeta of alpha is an eigenvalue of B. Hence, we can define the Pathstation matrix H of zeta alpha having an eigenvector X with eigenvalue equal to 0. X is directly connected to G, hence it brings information on the community structure as well. We show that for any degree distribution, the expected shape of this eigenvector X is precisely the vector of the solution, sigma 1 and minus 1, according to the label. It does not depend, its entries do not depend on the degree of each node. More clearly, here we consider the informative eigenvector of HR above for a different value of R, which is the one that was initially proposed, and below for R equal to zeta alpha, the optimal parameterization. Here we have a power law degree distribution. So the ith entry of the eigenvector in the first case depends on the degree, and this is well evidenced by the histogram of the entries of the eigenvector, which has a peak in 0, since for a power law degree distribution, most of the points will have a small degree. Whereas for us, we have a minimum in 0. When we apply k-means on these two eigenvectors, the second embedding, so the one we propose, generates a much better solution. And this is even more true when we're dealing with multiple classes. So h of zeta alpha, which is clearly connected to the non-vectoric matrix, has a 0 eigenvalue, which is the second smallest, which is informative. This is true as soon as it is theoretically possible to detect communities. And this eigenvector can be used for any degree distribution. So this connects B to h of zeta alpha thanks to the linearization of wave propagation. Now, another benchmark method for community detection in sparse graphs is the regularized Laplacian matrix, where instead of the degree matrix, we use d plus tau, the identity, where tau is the regularizer and the initial heuristic proposed regularization was tau equal to the average degree. So if we consider our Pathstation matrix h of zeta alpha, it has an eigenvector x with eigenvalue equal to 0. The same eigenvector, which is resilient to the degree distribution, can be written as an eigenvector of a regularized Laplacian matrix, where tau is equal to zeta alpha squared minus 1, which depends on the hardness of the detection problem, and is smaller or equal than c phi minus 1, which is close to the initially proposed regularization. With this in mind, we understand why regularizing the Laplacian matrix works in practice. We also understand why tau equal to c is a good choice, but we also know what is the minimal regularization needed to theoretically guarantee that there is detection down to the threshold. This was an aspect that was not at all treated in the earlier works on the regularization of the Laplacian matrices. So this allows us to connect also the matrix L tau. And finally, for easy detection problems, we obtain the classical Laplacians. As I said, zeta of alpha tends to 1 for easy problems. The Pathstation matrix becomes the graph Laplacian matrix in D minus A, and the regularized Laplacian becomes the random walk Laplacian. These two matrices have been studied extensively in the dense regime, and for easy tasks, they are indeed a good alternative to perform community detection. So here is how we see spectral clustering in sparse graphs and how we can connect all these different methods thanks to this parameter, the zeta of alpha, which is hardness dependent. Now, performance on real networks, here we are comparing different networks of increasing size. We are comparing the different spectral algorithm we talked about before. Our algorithm also allows one to estimate the value of k when it is not known. And here we are comparing the modularity. It is to be noted that our algorithm, which is the first column, always gets the best performance on all networks except on Wikipedia, where it is beaten by the random walk Laplacian, so not by another sparse method. In fact, it equals the L tau. And this network is a bit denser, so it's reasonable that it might be beaten. But in general, it outperforms all the other methods. So we contribute with a unified framework to understand spectral clustering in sparse graphs, in which sparsity and heterogeneity are properly kept into account, allowing to obtain the best performing algorithm on the networks we tested. We want to extend the studies on more structured graph, possibly time evolving, And to answer the question is if this hardness-dependent regularization a more general problem than just the community detection. These are the main references used for this work, and I thank you for your attention and for having attended my presentation. Goodbye.